In the long history of the Earth, it went through several massive ice ages. Become an ice age. The last ice age began about 260 million years ago. And it continues to this day. This period is marked by new cities and expansions opened by soldiers in the Northern Hemisphere, especially in North America, Europe, and Asia. During the Ice Age, global temperatures have dropped significantly, lead to the expansion of glaciers and ice sheets. These massive bodies of ice can cover vast tracts of land, even into the ocean. The growth of ice sheets is directly related to changes in the Earth's orbit and tilt, as well as changes in the intensity of solar radiation. A striking feature of the current ice age is the occurrence of ice cycles. That is, intense ice ages become ice ages. It alternates with periods of relative warmth that become ice spikes. And the last ice age became Moses Saint. Happened about 20,000 years ago. Ice caps covered North America at that time. The Daejeon region of Europe and Asia. Ice cream period. Most of the world's land is covered by ice. It dramatically altered the topography and the distribution of plants and animals. The ice sheet is so massive, so as to cause a significant drop in global sea level. Exposed road bridge, to move species between continents. With the end of the last weapon, it gets warmer. The ice should start to melt, cause sea level rise, and form the coastline we know today. The withdrawal process continues. The ice sheets of Greenland and Antarctica are remnants of once extensive glaciers. The impact of ice ages on Earth's ecosystems and the evolution of life was profound. Many large animals such as mammoths and saber-toothed lakes became extinct. This is due in part to human hunting, but also because of the dramatic changes in the climate that make it difficult for them to survive. Although the climate is warming now, but Earth is still in the midst of an ice age. Just ice from this ice age. The rivers do not cover as extensively as in the past these dramatic changes in the Earth's climate. Its transition from a large number of glaciers to fewer glaciers, known as the end of the Ice Age. These events are usually divided into three main stages, but determining the exact reality and endpoint of each stage is sometimes difficult. So how did the Earth enter the end of the Ice Age? During the Weapon period, the world's huge ice sheets and glaciers have expanded to their greatest extent, covering vast tracts of land and sea, and eventually something causes this ice to melt. Marks the end of ice cream. The process by which this ice cream ends is called end time. It is usually divided into three stages. The first stage is called the retreat night. The slow but continuous rise in global temperatures signals the beginning of the end of weapons. Usually lasts for tens of thousands of years. This process is often driven by changes in Earth's orbit. Becoming a Milankovitch cycle. These cycles are mainly designed to change the angle of the Earth and its orbit around the Sun. The first Milankovitch cycle is eccentricity. Describes the shape of the Earth's orbit around the Sun. This can change from a perfect circle with an eccentricity of 0 to a more elliptical shape, up to about 0.067. The current eccentricity of the Earth is about 0.07. So our orbit is pretty circular. However, when the Earth's orbit is more elliptical, the difference in solar energy or radiation between the nearest and farthest points varies significantly. The periodicity of this eccentricity cycle is approximately 100,000 years. The weapons of the past, the spikes, are highly consistent with this cycle, about once every 100,000 years. The other key Milankovitch cycle is the tilt of Earth's axis. As the Earth revolves around the Sun, its tilt angle oscillates between 22.1 degrees and 24.5 degrees. Complete a complete cycle from smallest to largest and back to smallest. About 41,000 years. Changes in tilt also affect the distribution of solar radiation received by the Earth. Lead to long-term climate change. As the tilt of the Earth increases, during the summer, more polar regions are exposed to solar radiation, causing the ice sheet to melt rapidly, and it has a feedback effect on the global climate. Analysis of the past 800,000 years shows these events are strongly linked to the end of the Ice Age. The current axis cleanliness is being minimized. This should theoretically reduce the melting effect on the ice. Another factor is that the ground is turbid, affects the relative timing of the seasons and the Earth's orbit around the Sun. The built-up timescale is about 19,000 to 23,000 years. And aligned with the regularity of the final event. Although the correlation is not perfect, but it appears that a combination of these factors drove the end event. These Milankovitch factors create a feedback loop, contributing to global warming. As the ice melts, exposure to more marine or land surfaces absorb more sunlight, lead to further warming and melting. This process accelerates, pushing the Earth into a period of rapid warming. Become a full-scale promoter. This stage usually occurs within a short period of time. Significant ice melt and sea level rise typically occur within a few decades. The release of greenhouse gases such as carbon dioxide and DEX, previously dissolved in the cold ocean or permafrost, driving further warming. Ocean currents that accelerate this process and reorganize. Only after the second rapid warming phase, global temperatures are just starting to stabilize, marks the beginning of cum weapons. That's where we are. During this period, the ice sheet stabilizes and shrinks. Sea level reaches equilibrium. As the temperature rises, the abdominal feedback loop becomes more pronounced, like being covered in ice on the chest. The growth of plants in covered areas. This plays the role of the carbon club and carbon dioxide from the atmosphere through weathering processes. These processes help stabilize carbon dioxide and temperature levels in the atmosphere. This is the state of our current climate. Why is the deck level rising? And how he measured it. Scientists are shocked by the rise in deck levels in 2020. Despite COVID-19 pandemic lockdown leading to cleaner air. Reduction in carbon dioxide pollution. Methane is a gas that occurs naturally around us. In the wetland ocean. Even in the digestive systems of cows and other animals. It's colorless and odorless, but it's a potent greenhouse gas. This means he is very good at capturing heat from the sun. In the 1980s, with the prosperity of the natural gas industry, deck level rises sharply. But by the 1990s, these levels tend to stabilize. However, in the mid-2000s, scientists have noticed a curious thing. Methane suddenly starts to increase again. What's going on here? It turns out, determining the source of methane dissolution is not always easy. Unlike carbon dioxide, which mainly comes from burning fossil fuels, methane comes from various natural sources. What scientists know is that methane remains in the atmosphere for about 10 years. Then it will decompose, and when he was in high school, he's very good at capturing heat. 80 times stronger than carbon dioxide. And that's because the chemical structure of methane acts like a perfect endothermic machine. Especially in a specific wavelength range, can easily escape into space, so methane doesn't have as long a life as carbon dioxide. But its ability to absorb heat makes it a major contributor to climate change. The molecular structure of methane makes it highly efficient in the wavelength range of approximately 3.5 and 8 micrometers. The absorption and emission of infrared radiation, that's a range that coincides with exactly one atmospheric window, allowing radiation to escape into space. In comparison, carbon dioxide absorbs radiation in different wavelength ranges, and these wavelengths have been effectively absorbed by the atmosphere. This makes methane's contribution to the greenhouse effect even more significant. In recent years, due to the advent of advanced technology, our ability to detect the source of methane has improved significantly. Ability to identify emission margins from ground and space. One particularly interesting approach is to aim the laser at the ground. Tuned to a 3.5 or 8 micron wave field. When the laser beam is reflected back, can be used to map global deck levels. By analyzing the absorbed light, researchers can identify areas with high deck concentrations. Take advantage of this technology. NASA's Jet Propulsion Laboratory detected a giant deck is seen above a landfill in Iran. Reserved deck for discharges exceeding 8,500 kilograms per hour. However, this is compared to a super archway chicken flock in Turkmenistan. The flock is associated with oil and gas infrastructure. A total of more than 50,000 kilograms per hour. The findings recently published in Global Biogeochemical Cycles show that due to rising temperatures and carbon dioxide levels, methane emissions are increasing in tropical and wetland regions. This causes the growth and decomposition of organic matter to accelerate. Methane emissions go up, green leaves go up. Permanent Dongpu district stores a large amount of carbon. As they thaw, release trapped organic matter. It also contributes to methane emissions, although modern landfills typically have methane recharge systems. But not all methane is captured. The opposite sex is still released into the atmosphere. Fortunately, methane detection technology is being investigated. Identify leaks and collect methane emissions from oil and gas infrastructure and landfills. This is mainly driven by economic motives, because recharging and harnessing methane generates revenue. However, there is also the benefit of reducing greenhouse gas emissions. So what does this all mean for us? Since 2006, agriculture and waste sources account for about half of the increase in methane emissions. The other half is thought to be caused by natural biological processes, in particular wetland feedback loops drive. And here's the interesting thing. Although current global biomethane emissions levels remain within normal historical limits, but the speed and acceleration of this trend is extremely high by all historical standards. Even during the rise driven by fossil fuel use in the late 19th century, this change in the composition of methane could be good news that nature has not seen in recent history. We are increasingly able to identify the sources of these methane emissions. The challenge is that we don't know where this trend is headed. So what if nature itself was producing the methane, rather than direct human activity? Then it may be more difficult to slow down or intervene in this process. Replenishment methane is also very tricky than trying to get CO2 out of the air. This is in part because methane is much less abundant in the atmosphere than carbon dioxide. Well, there are ways. If porous minerals are used to convert methane to carbon dioxide, but these methods have not been widely explored. Because at the moment it's not very useful to produce carbon dioxide. However, if it means reducing the release of more potent greenhouse gases into the atmosphere, it might be worth doing some development in this area. If we want to establish permanent self-sufficient settlements in space, then these communities need not only to be self-sufficient in food and air circulation, it also needs to be self-sustaining in terms of population. To do that, we need to figure out whether we can successfully reproduce in space. What challenges will it face? If you give birth in this unfamiliar and dangerous environment, how will the fetus develop? If children grow up in an attractive force environment, obviously it has an impact on their limb and muscle development. It's basically evolving into another branch of our species, so to speak. We Homo sapiens evolved on Earth, the densest planet in the solar system. All Earth species have adapted to relatively attractive forces. We don't yet know the effects of living in a low attractive force environment for a long time, but preliminary findings are worrying. Astronauts living in the dangerous gravity environment of the International Space Station must exercise up to 2.5 hours a day to maintain the physical fitness to function normally after returning to Earth. For longer liftoff missions, designers plan to rotate the members of the spacecraft to expel parts, has produced an effect similar to an attractive force. Let it go down and out along the axis of rotation. But we don't know if the attractive force of this simulation can fully protect space travelers. Simulating additional attractive forces on the surface of a planet would be very difficult. Our species was born on a planet with a strong magnetic field, Earth. Earth's nuclear dynamo projects a barrier outward. Protect all life on Earth from harmful radiation. Perhaps the moon and other small celestial bodies are not so fortunate. They have little natural protection against the high-energy particles emitted by the sun. This has effectively stripped Mars of most of its atmosphere. From the supernova explosion, high-energy cosmic rays from self-selecting neutron stars and jet black holes keep invading us. As the solar system moves away from the Earth, these powerful sources of radiation are particularly dangerous to developing fetuses and young children. Many of the environmental factors in space that are harmful to adults are more harmful to children and fetuses, including radiation and dangerous gravity. Therefore, we need to determine whether these factors harm the developing child, or whether additional protective measures need to be added. It may not even be able to reproduce successfully in space at all. However, the biggest problem is that we don't even know how to study in a comparable way whether humans can reproduce in space. Because this kind of science involves pregnant women and fetuses. And that's generally considered grossly immoral. We haven't seen babies born in zero gravity. I don't know what the impact will be on the child's bone density. This is when they absorb minerals into the bones, rather than the stage of gradual mineral loss in adulthood. For children, this could lead to serious health problems. But we don't yet know what these problems are. On a planet like Mars, settlers may be forced to live underground or in structures with thick protective layers. Some space architects believe that structures can be 3D printed with locally collected rock cement It uses transparent water as a barrier to let natural sunlight through, due to the weak radiation at low angles. The windows behind the rotary structure provide views of the original landscape. But brief outings on these desolate surfaces will always be fraught with risk. Let children live on a planet they cannot directly experience. Can't even grow without stress charms. Is it fair to do so? If children grow up in such a world, may never return. Earth then. Who decides what environmental conditions are suitable for children? Astronauts who have lived in space for a long time often encounter many physical problems when they return to Earth, especially in readjusting to the Earth's attractive forces. This worries us. If a child grows up in space, they may never develop the bone and muscle structures necessary for life on Earth's surface. This means that children who grow up in space may never be able to return to their species' home. So this raises a huge ethical question. Is it wrong to raise children in an environment where they cannot return to Earth? On the other hand, it could also be a security risk. We have very strong cultural beliefs. Parents should be able to make decisions for their children. On Earth, parents already have to make similar decisions for their children. Refugees take their children on an extremely dangerous journey to bring them to a new place. Knowing that he might never be able to return to his home country, humans have been making these decisions for their children for generations. Children may not be able to return to Earth and adjust to normal attractive forces. Indeed, it is something that any responsible parent needs to consider. But we also have to face the truth. There are all kinds of disabled people on Earth. We don't call their lives worthless. We think they can also have a good life. So maybe a man who only lived on the moon. Although it is impossible to visit the Earth, but you can still have a good life. People often find technological solutions to meet their needs. If you work out in the gym, or a 3-hour workout on the space station at the right level for Earth's normal attractive force, maybe we can mitigate some of these effects with clever engineering. If through clever design, we can address these risks, growing up in these challenging environments can be full of amazing adventures. These children in space may encounter unprecedented wonders and challenges. Their ability to adapt to the space environment may one day exceed that of Earthlings. Whether it is biological modification created through gene editing, mechanization and neural implants, or external enhancement, these future generations in space could multiply and diversify in ways we cannot currently imagine. But are we mature enough to handle future differences? Humans on Earth have a certain exclusivity towards other species. There is uncertainty in the attitude of people from the space environment. They will indeed be different in some way. I don't think any of this will be the deciding factor in preventing humans from migrating to space. But there will inevitably be some collateral effects. The final ethical issue will revolve around those who choose to give birth to their first child in a space habitat. It's inevitable. If we really want to separate as a civilization from the Earth, there will be people who are willing to take risks and start a family in a new environment. We need to go deep. But that's part of the evolutionary process that we're going through right now.